Hello. I couldn't do this one yet, so this will be interesting. All right. Yes, the contest was interesting, I think. Q4 was not easy to me. All right, so let's get started. Let's start with question 1. Hey, Sarah, how's it going? Okay, just cover with part 1. Array is called special if void of all of its elements is at least k. Return the length of the shortest special non-empty subarray or -1. Okay, so this is the easy one, so probably we can try all the subarrays. So yes, the size is 50. So we can go over all the subarrays and just the shortest. Find the shortest, or -1 if it doesn't exist. So we can just we want the shortest, so the minimum. So let's initialize to infinity. Then we start. We start the subarray at I, at position I, and we're gonna be going over all the elements from there. So notice that once the OR is already greater than or equal k, if we keep growing the subarray, then it cannot decrease. So once it's greater than or equal to k, it will stay greater than or equal to k. So we can just, so here we OR our current OR. So this is to do this in quadratic and not cubic. We want to keep track of the OR. So this is nums of j. And now if cur is greater than or equal to k, then we found a subarray, as they call it, special subarray. And so we want to consider the minimum length. So our subarray is length j minus I plus 1 because both ends are inclusive. But now we can break, because like I said, if we keep going, then they all will be special, but they will be longer, and we want the shortest. So we don't have to keep going. I mean, it's not that it matters. So the solution is still quadratic. And here we want to return -1 if res is inf, else we return res. So smart code, welcome. So this should work. It does. Cool. So let me share. Computer. It's a little slow. Let me see if I can close a few things to make it respond faster. So maybe we can do Q3 before Q2, because this is part 2 of Q1. So that is part 2. So it's the same problem, but now the size is up to 2 times 10 to the 5 to the 5th. So this should ring a bell. So I say that I wanted to teach deep patterns. So here we have a subarray or a window, right? And we want to grow it from the right, and we want to find out the shortest window such that it satisfies the condition. But if the OR is greater than k, greater than or equal, we can decrease it. We can increase the left side of the window until we get to the end, until the condition is not satisfied anymore, and that's going to give us the shortest window. So this is a typical sliding window problem, right? So we can do our usual sliding window. I will assume that you are kind of familiar with the... Well, let me just refresh it. So usually my template, so here we're gonna have we're gonna keep track of the OR of the window, right? So this is our window, and then we're gonna have a left side of our current window, and we're gonna have the result, which is infinity. So we want to go, we want to crack all the endings of our window. So here I'm going to use some pseudocode. So here I want to add nums of R to our window, right? So let's to the OR. So we add it, but now maybe we have to shrink the window from the left. So L, we want to have a window that is not empty. So if the window is not empty, which means that L is less than or equal to R, because our window includes the if our window is not empty and we have an OR that is greater than or equal to k, then we remove nums of L from the OR of our window, and we shrink the window, increase this by 1. So we want, so I'm using greater than or equal because if we have many elements, so let's say that we're at R and here's L, and let's say that the OR here is k, but if we extend it here this is also k. So I want to go until the condition is not met anymore, so that I guess you could do this in different ways. So I want to do it in a way so that L minus 1 is the index, the first index, such that it is well, the closest to the R, the smallest window, such that that this condition is met. Okay, Glamp, welcome. How's it going? Okay. So then here I want to know that there's a, so I'm assuming that L minus 1 is the closest position to R, such that the OR is greater than or equal to K. So that means that L minus 1 has to be greater than or equal to 1. Otherwise, there's no solution, right? And now we want to get the minimum of the length, which is going to be L minus 1 plus 1. Okay, because this is my index. Maybe it is confusing that I'm using L minus 1, but that is the index that, like I said, is the closest index to R, so the shortest window, such that the OR is greater than or equal to K. Okay, so, and since the indices are inclusive, we add a 1 to them. Okay, so this is all good, but there is a problem here, that the remove part is a problem, because think about it. So we're doing a bitwise OR, right? Hey, Whale, welcome. We're doing a bitwise OR, so let's think about bits. So let's say that you have 6, and then you have this, and so on. You have these numbers. But let's focus on, so this is bit 0, this is bit 1, this is bit 2, and 3, and so on. So let's focus, when you're doing a bitwise operator, usually it's better to think 1 bit at a time. So here, let's think about, I don't know, this bit, right? And so this is 1, 1, and 0, right? So let's say that this is our current window. And we want to, so L is here and R is here. But we want to remove this, right? But notice that we don't know if what the OR of this is going to be, right? If we remove the 1, maybe if there are, it depends on what's here, right? If here there are all zeros, then yes, when we remove the 1, we're gonna get an OR that it's 0 at this bit. But if there is at least a 1 or more, then we're gonna get a 1. So we cannot. So it's not like when we have a sum of the window, then we can just subtract nums of L and so on. Here we need to know what's in the window that is left. And so maybe what we can do is to keep track of this sum in the window. So for each bit we can keep track of the sum of the ones, right? So now for this bit, we said that this was bit 2. So for this bit, we're gonna have the count of 1, no, sorry, so we have two ones here, right? This one and this one. And when we remove this one, now we have 1. And if the sum is greater than 0, that means that that bit is going to be 1. And only if the sum is 0, it's going to be 0. Okay, so that's how we're gonna do our operations. Our add and our remove are going to be the sums of the window, but for each bit. Okay, is that clear? Let me know if it's clear, and otherwise I can explain a little more. So let's write down the template. So remember that you usually want to do your template. So you don't want to change it too much. So this is just what I wrote there. So we're gonna add, and let's say we're gonna keep track of the counts for each bit. So these numbers are up to 10 to the 9. So that means that, remember that 2 to the 30, it's the first power of 2 that is greater than 10 to the 9. So that means that we can have bits from 0 to 29 inclusive, and that's going to handle all the bits in these numbers. So this is going to keep track of the count in the window for each bit, of the sum of ones on each for each bit. Okay, so we add to our counts nums of r. Okay, and then while L is less than or equal to R, and the OR, we're going to have a function, an operation that gives us the OR of the current window. So the OR of C is greater than or equal K. This is what I wrote. And then if that's the case, we remove nums of L from C, and then we subtract, we add 1. Sorry, we shrink. So then here we said L minus 1 is going to be our index, so we want this to be part of the array. And here we want the minimum between, so this plus 1. Okay, so here we want rest to be infinity, and in the end we're gonna return minus 1 if rest is infinity, else we return rest. Okay, so now we're down to our bitwise operator. So notice again, this is just the template. This is just the sliding window template. So now we have to deal with the bits. So we have an add, we have an OR, we have a remove. Okay, so let's add. So notice that adding and removing are pretty much the same, but we have a delta. We either add 1 or we remove 1. So let's do it this way. So let's have a delta, which by default is 1 because we're adding here. And then we're going to have a remove that just adds, and the delta is minus 1. Okay, so that's how we reuse functions. So here we want to go over all the bits, and we want to add 1 to the count of the bit here. So the bit is Yeah, well, actually, if this bit is on, we want to add delta to the bit. Okay, and now we have our OR of the counter that is going to be, so we go over all the bits, and if the count of this bit is not 0, then we just add that bit to the result. Okay. Yes, this sounds good. Passes the examples. And it is accepted. So let's share the submission. Is this how you guys solved it? I like how we how I encapsulated the bitwise handling in functions so that we keep our, let's ruminate so that we keep our template pretty much the same. Yes, this is just, so remember that so here I'm adding, this is just to reuse the function to not duplicate this code, right? So if I'm adding, I want to add 1 for each of the bits that are on in X. So I'm adding X to the window, right? So that means that I'm going to check, I'm going to go over each bit, and if that bit is set, I'm going to add 1 to the count of that bit. Do you follow that? Well, it's not turning on or off. So we're counting how many bits there are on in the window. So that's what we're adding. We're not turning. So here we check if X, this is the usual way to check if a bit is set. But then if that bit is set, here we add the delta, which is 1 or -1 in the case where we remove. Okay. Then here, when we do the OR, we check for each bit if the count is not 0 for that range. That means that in the OR of the whole range, that bit will be set, will be a 1, and this is the position of the bit of the I bit. Okay, so any other questions? So yeah, this is what I explained here. Let me know if you want me to go over this a little more. So I think the contest you could have solved it. The problems are exactly the same, except for the constraints. So you could just reuse the code for Q3 on Q1, and you maybe saved some time if you were confident that you were going to get Q3. Okay. So now, where is Q2? Here. Okay. So now let's go to Q2. So this one, yes, I didn't get this one, why it is a medium. I think it's pretty straightforward. I mean, it's based on, well, let me just read it to explain it a little bit. So this is, the story involves a game, right? You have levels, 2 players, and some levels are possible and some levels are impossible. And a player, when a player clears a level, it gains a point, and when it loses a level, it loses a point if he doesn't clear it. So and they're going to do. So the first player does some number of levels from the beginning. The 1x, and the other one is the suffix for the corresponding suffix. And so we want to know the minimum number of levels that the first player should play so that he gains more points than the second player. Yeah, here the maximize their points. Yes, I guess this only means that when a level is possible, they will clear it, so they would gain a point, and when it is impossible, they won't. And if it's not possible, we return 1. So this is just a classic prefix and suffix where we go from left to right and we keep track of the sum of the points for the left side, and then we keep track of the points for the right side, which we can subtract, right? We can have the total points of the. So let's one way of simplifying this. So you have 1 or 0 here, but 0 means that you subtract 1 from the points. You subtract 1 point. So maybe we can just go over the elements, and we just replace the zeros by minus 1s, so that it's just the sum. So we're gonna keep track of the left sum and the right sum. Okay, and now we want to go over, but remember that each player must play at least 1 level. So we want to go from 0 to I inclusive. That's going to be the number of levels that player 1 is going to play. So that means that we have to get up to n-2, right? Inclusive. And so now we want to add the current level to the left, and we want to subtract the current level from the right. Yeah, I guess we didn't have to. We don't need to have this. We could have. Yeah, but I think it's simpler this way, because you know that the points of the total points, you can subtract the left and you get the points that the right would get. But I think it's simpler this way. So here, if the left is greater than the right, that means that we found a solution, the shortest, the minimum number. So it's I plus 1, and here we return minus 1 if we haven't found any. Okay, so we pass the examples. And we're done here. All right, any questions? I think that one was kind of an easy one. Okay, so if there are no questions, let's go to the hard one, to Q4. So you're given, find the sum of subsequence powers. So powers is a very misleading term because they are just, the power of a subsequence is defined as the minimum absolute difference between any, the spicy problem. Yeah, it took me a while to get this one. So the power of a subsequence is defined as the minimum absolute difference between any two elements in the subsequence. So it doesn't have anything to do with powers, math powers. It's just the minimum absolute difference. So return the sum of powers of all subsequences of nums which have length equal to k. Since the answer might be large, okay, so let's write this down so that we don't forget. And of course the sizes are, oh well, the size is pretty small here, so this is a hint. So when you have 50, size 50, it means that you can even get away with a n to the 4th power. Whoa, what the? Because 50 to the 4th is 6 million, which is within the range of what you can do in LeetCode. So that gives you a hint of what might work, what might be expected. Can you zoom in? Well, here, you mean? Or I think this is already pretty here. Okay, so maybe we can work out an example. So there's a technique that sometimes works for, so there are problems where they tell you to count the number of subarrays or subsequences such that and they have there is a value associated with each subsequence or subarray, which is the minimum or the maximum, which is the case here. And so that means that you can try all the values, all the possible values for the minimum here, and then we can try to count all the subsequences that have that minimum. And so we multiply the number of sequences times the minimum, and that's going to give us what we're asked to do. Okay, so here maybe we can start doing, so notice that since these are subsequences, these are subsets, essentially. So the order doesn't matter. So we can sort them. Okay, and let's consider all the absolute differences, right? So let's call them diffs, and we're going to make a set because they could be repeated. So we can go over all the pairs, and we do this. Okay, so now we have all the possible absolute differences. So what I say is that, so this is already can be n squared, right? So let's keep track of that. So here we're gonna do the mean diffs from the possible differences. We want to now count how many subsequences there are that have this mean diff. Okay? And for that, we're going to use dynamic programming, as you might have expected. So in dynamic programming, so notice that you can do a take it or leave it kind of dynamic programming, where you are where you decide whether each element, if you add it to the subsequence or not. Okay, but there are a lot of special things here to take into account. It's not that easy, at least in my solution. So yeah, maybe we can work out an example. So yeah, maybe even this one is okay. What we did so far was consider all the differences. So let's say that our mean diff is 2, right? So here, if we do 3 minus 1, the absolute difference is 2. I realize sorting might help when all sequences of type will have the same power, but it's still TLE. Oh, so you tried this one? That's brave. I think only 200 people solved it. Well, now it grew. I don't know in the contest how many solved it. Maybe if we go here. I was close to solving 3 and 4. Okay. Nice. I mean, you 4, are you sure you were close? I mean, it's pretty tough, I think. Okay, so I don't know how to see how many people solved it in the contest, but never mind. Okay, so let's say that the mean diff is 2, right? So we're gonna go over. Let me send the solution. Yeah, we can do that offline. So we have the array sorted, right? So we want to count how many there are that have length 2, right? So we start at the beginning, right? So this is I, where we start at the beginning, and we can decide whether we add it or we don't. We add 1 or we don't to the subsequence. But if we add it, notice that we can't add 2 if we added 1. If we add 1, we cannot add 2, right? Because that would make the mean difference 1, but we want the mean difference to be 2, right? So if we add 1, we have to skip here. We have to go up to 3. right? Because that is the first element, such that the difference between 3 and 1 is 2, which is our mean diff, our current mean diff. So every time we add an element, we have to make a jump to the next element that has a difference greater than or equal to our mean diff. So we can try to pre-compute that. So we can go from right to left, and we can try to pre-compute with 2 pointers, which is the next element, such that it satisfies this condition. So let's start by doing that. Well, notice that if the mean diff is 0, then it doesn't matter, because we're gonna multiply. So the power in that case is 0, so it adds 0 to the result, so we can skip it. I mean, I don't know if we need to, but let's do it anyway. So let's go from right to left, and let's keep track of, we can do this 2 pointers thing. So we want to know, we want to set up an array that is going to tell us for each position what is the next position where the difference, the smallest position, such that the difference between this position, the value in this position and the value at I, is greater than or equal to mean diff. Okay, so here we have a 2-pointer solution. So we want to check if j minus 1 it's already satisfies the condition, right? So for that, j minus 1 has to be greater than I, and nums of j minus 1 minus nums of I is greater than or equal to mean diff. So if that's the case, we can move closer to I, and that means that our next index from I is going to be j. Notice that it could be that we have to go outside of the array, right? If j is n, that means that all the elements that are to the right of I have smaller distances, smaller differences than the minimum. You know, get to the next elements once we add an element. Okay, but there's another catch here, which is, I think, what makes this complicated, a little bit complicated. So if we do this jump, then we guarantee that we're not going to have any difference less than mean diff. Okay, that's handled already. But we also we want to count all the subsequences that have a difference equal to mean diff, right? It doesn't count if there is no difference equal to the minimum difference. In that case, that wouldn't be the minimum. So we need to keep track of whether we had any difference that is equal to the minimum. So for that, what we do is we're going to keep track of 2. So our state is going to be, well, I, which means that we are at position I. Then, of course, k, we need to choose k elements in the subsequence. And then we're going to have this done variable and this, how do we call this? Can, let's call it can. Okay, so done will mean that we already have a difference in the subsequence that we are selecting. We already have a difference that is equal to the minimum difference. Already have a difference diff equals to min diff. Okay, so this is going to keep track of whether, so if we don't have it, so if done is false in the end, then that means that we haven't created a subsequence that satisfies our condition, the condition that the minimum difference is 2. Okay, and then can is a little more complicated. So can is going to tell you this. So for example here, if we're at I is at 1 and we jump to 3, right? Because we know that we have to skip 2. And here we know that the difference between 1 and 3 is the mean difference, right? So can is going to tell us whether if we add the current element, the element at I, if we add the element at I, then we will have a difference equal to the mean diff. That's going to this is what this is going to tell us. So initially it is false. So this is how we're gonna set done. If at any point when we can add an element that will give us the difference, the minimum difference, then we set done to true. Okay, and that is essentially the idea. I don't know if it can be done simpler. Maybe it can, but this is what this was my idea. So now we can do memoization. So we want to count, and we want to have I, K. So the done and the can. Okay, and notice that we're gonna call this with no, this is not here. This is here. Okay, so finally, so we're gonna implement this, and then we're gonna add the count. So starting from index 0, we have to add k elements to the subsequence, and then let's say this is false and this is false, because we haven't added the difference of min diff yet, and we cannot add it by adding the current element, the ith element. Okay, so we mod, and notice that we have this memoization, right? But every time, for every loop, so this function is going to depend on the min diff, right? Because it's going to depend on this next element that was calculated based on the min diff. So every time, every iteration, we have to calculate the count again. So that means that we need to clear the cache. So we can do this, and then we're gonna, on every iteration, we're gonna do this. So notice that this is fast enough, because here, like we said, diffs can be at most the square of nums, and here the number of subproblems is going to be, so these two are n squared, and these two have are only flags, are only booleans. So that means that we don't. That means that the number of iterations is going to be n to the fourth, which is what we calculated at the beginning. That was good enough. Okay, so here we return the result, and so here let's think about the cases. So here, if k is 0, it means that we already selected all the elements of the subsequence. So now we want to know if we were done. If we were done, so we have the min diff, then there's one, we found one subsequence, else we found 0 subsequences. Okay, then if we are out of elements but we haven't selected the k elements, then there are 0 subsequences. Okay, so now we're at the take it or leave it stage. So let's say that we leave it. Okay, so we're gonna, so if we leave it, we go to the next element, and we still have to select k, and then is going to stay the same. But here there's a can is a little more complicated. So let's call this can2, and let's do can2, because if we could get the min diff by adding this element, but we skip it and we go to the next one, but it turns out that the next one is the same, then we still can add it and create the difference, right? So that means that if we can here, and the next one is the same value, then we still can do it. So now we're at the take it stage. Okay, so now our next, let's call it I2, this is going to be the next element where we can keep adding elements to it. We do the jump that we discussed, and then since we're going to take it, if we can, so done2 is going to be either done or can. Okay, because if we can make the mean difference adding the current element and we're taking it, then we're done. And then here can2 is going to be, it's going to depend on whether we so if I2 it's within the array, and nums of and the difference is equal to the mean difference, then we can do it. So now we just add this. No, this is I2 and k minus 1 because we took one element, and then this is done2 and this is can2, and here we mod. And we return res here. Okay, I think this is it. So so we didn't define res. So what we did wrong here? So let me check. If it's done, then it's 1, other one's 0. This looks correct. Here, here, if we could for this element and the next element is the same, then we can for a plus 1 as well. That's correct. Here we go to this element, and done 2 is going to be this, and can 2 is going to be either I2 less than n, and the difference is equal to the min difference. Yes, this looks correct. So maybe this is wrong. Maybe something here is wrong. What is here? So j minus 1 has to be greater than I. That is right. N nums of has to be greater than or equal. This looks all correct to me. Did I sort? Yes. I sorted. If it's 0, we skip. Here, this looks right. It's less than n2. Oh, I forgot to multiply by min diff. Okay. Are we choking? Coach, why do you like to point it out, right? Maybe you can be more positive. Okay, so we got it. Easy work. GG. Okay, so yeah, I think it, once you get the idea, it's not that complicated. So you have to understand what these flags mean. But other than that, it's just take it or leave it with this with this idea that we have to skip elements. So I don't think it's so complicated in the end. So I had to, so first I did this without the flags. Yeah, without the flags. But then I had trouble double counting. So that's why I introduced the flags, so that I could count. Because before I was, instead of having the difference, I was having the indices of the two elements that had that difference. And I would make sure that I would add them with the, but then you double count, because the fact that you have that difference doesn't mean that you might have that difference in some other elements. And then when you consider those other two elements here, then you might count this more than once, the same subsequence more than once, and that's why it was wrong, and I had to use these two flags. Okay, so that is it. This was an interesting problem, I think, and the other one as well, the Q3 was interesting as well. I mean, it's a variant of so the sliding window problem and doing the OR bitwise for a window, but I think it was an interesting combination. So that's why I think I try to explain the pattern of the. That's why I first used the template of the sliding window, and then all right, so yeah, that's all I have for now. See you probably tomorrow for the stream of the weekly contest. So bye bye.